Hi, this is Matthew. I'm going to be our team spokesperson for today, and we are presenting our device called Hardcore, which stands for Handheld Assistive Removal Device to Capture Observable Regolith Elements. Yeah, we're good. Okay, so here's a picture of our organization. We are part of a bigger team. We're a subsection of a bigger team called the Columbia Space Initiative. This is a team of students around our campus who are just interested in all things space. And here's a picture of us gathered around alma mater on our campus. And here's a look at our team. We have 6 active members, and I'll run through the names now. I believe most of us are here in the call as well. Elizabeth, Cal, myself, Matthew, Javier, Swati, and Eric. And together we've been working throughout the last 2 semesters as well as virtually once we were sent home a little while back in March. So we'll get started here with the device overview. So on the left is a CAD model, a representation of our device. Later on in the presentation, we will show some images of the real device, as well as a video, which we can maybe just skip through for a few short clips to get a better understanding of what we're working with. So our device features a coring bit, which can be detached and is separatable from a stabilization jig, which is used to keep the device upright and safe during operation. And broadly speaking, the assembly is used to capture, collect, and retain lunar core samples. The way the device functions is that there are 2 plates. As you can see, one rectangular upper plate and the circular lower base plate. The upper base plate lowers itself along the rods when downward pressure is applied through the handheld drill. And there are compression springs, 2 compression springs, one on each side, that are used to allow the bit to return up to its original position and also to help with assistive features such as helping with mitigating drill walking due to the extra pressure that the user can apply when lowering that drill for initial contact. We have featured a rounded base plate design with small feet along the edges to maintain stability during the drilling operation. And in addition, this is an optional add-on, but we also have a external storage belt if the diver for testing wants to use our temporary kind of storage device. So we can move on. And so there on the left are some pictures of the device. The upper picture is the belt that I was referring to with small plastic capsules in which these samples can be contained. These are all attached through Velcro. And as well as on the lower left there, that image is the labeled version of the complete device. So the way that the coring process is carried out is that first the drill shank, which is removable and is inserted through a bearing on the upper plate, can be inserted from the bottom upwards, and then the drill shank can then be accessed from up top. At that point, the user can then attach the drill chuck from that access point. During operation, the base plate should always be aligned as stably as possible along the sample surface and parallel and flat as possible for the operation. Aside from that, the operation is essentially that of just a normal coring bit in which slow pressure is applied downwards. On the final model, there is a black marking for the 3-inch stopping point for the user. But at the same time, the coring bit also opens up a bit in diameter and will mechanically stop itself once that 3-inch mark has been reached. And at that point, the device can be extracted out and samples can be removed and inserted into that belt, or kept within the drill bit itself and then just brought back up in a non-water environment or a non-EVA environment. We can go to the next slide from here. So here's an updated look at the device with a few add-ons, mainly off of safety considerations. First of all, a red tape was added to the device to note a potentially hazardous area. Fingers and hands can be kept safely on this part of the device, but we want to avoid having fingers and hands go within the device. So we've just marked this ring red just for extra safety. In addition, as noted by the number 2, we have added blue nylon, which is used to wrap around the springs, and this will prevent users from entrapping their fingers or gloves or other material within these springs. So the springs can still function perfectly fine. We just have that outer nylon coating to keep things safer. In addition, we have added on a removable rubber cap that goes on top of the coring bit tip. And so for transportation or when stowing the device, the user's gloves will not have the risk of tearing on the sharper coring bit pieces. And this cap can be removed once the user is ready and comfortable for the drilling operation. In addition, we've taken extra attention towards filleting corners on the manufactured parts of the device and also on covering edges with safe tape along other parts of the device that could pose extra risk towards damage. And lastly, we added a eye bolt towards the end of the device, which serves as a secure tether point specifically for testing operations, which is out of the way and avoids entanglement with the rest of the device. And we can proceed on to the next slide.
So real quick, you had mentioned that some of these changes were based on some of your safety assessments. Are all the updates in the TDP, or did you change anything since what you submitted?
That image is the final update, but we do later on in the presentation go into a more precise hazard analysis. But that image before does reflect the current device.
Okay, and if there's any other information that needs to be updated, please send that to us when you're able. Appreciate it.
Okay, absolutely. So here are some technical details on our device. Just generally speaking, things like weight, dimensions, and so on, as well as materials used. Something to note is that the eye bolt is above that 6-inch limit, but within the cylinder requirements, the 6-inch diameter cylinder, it does fit successfully. And we can go on to the next slide. So here's a breakdown of the different components on our device. The stabilizing jig, which can be separated again from that coring bit, which features the 2 plates separated by springs. The coring bit itself, which functions on its own, but works best in tandem with this stabilizing jig that we've designed. In addition, there is the eye bolt handle. The way that this eye bolt attaches onto the device is through a simple screw-in mechanism, and it will hold during testing. This addition is needed because in its standard configuration, it does not fit within the dimension requirements, but it can then be, after stowage, it can be opened up, tightened on, and then used properly. In addition, there is the belt storage system, which is an extra add-on if during testing we find it necessary or a good idea to try more samples. And lastly, a pair of pliers, which serve as a tool to remove coring samples from the drill bits. Earlier in the presentation and later on, I believe it'll come up as well, there are small holes on the side of the coring bit, which help to remove debris through the operation, but also provide an access point for these pliers to reach in, grab the sample, and slot it out of the coring bit. And we can move on. Here's a breakdown of the materials that we'll be using. As far as we have tested, all materials work and function well underwater and pose no significant concerns. And through our various tests, we have seen no concerning evidence of any kind of wear down or damage. You can go to the next slide. So now we will go through a breakdown of the operations plan and how exactly the user can use this device safely and effectively. So there are two phases or two transportation modes in which the device can be operated. First, the transportation phase, which is the stowed phase or the essentially smaller in volume phase. The eye bolt is removed and stored upright, slightly diagonally, and the caps are placed over the drill bit, both on the bottom as well as on the top, to avoid the drill bit from falling out. Meanwhile, in the operation phase, the caps are removed, the eye bolt is fastened into the device, and the object is then ready for use. The storage belt can either be worn in some way on the diver, as it's suited for wrapping around the waist or possibly around an arm, or it could simply just be tethered in some location nearby the diver, depending on the needs. I mean, we can go to the next slide.
And so do you have a preferred method of operating, like how you want this evaluated in order to get certain data, certain information back to drive your design?
Yeah, ideally we would like to attempt at least extracting 2 samples in order to see if that extraction phase or that extraction out of the drilling bit is feasible during testing. And we can then also assess just 2 different samples to get a better idea. However, we also recognize that maybe realistically, 1 sample is what we can reasonably get out of the testing session. So we're prepared through our readout procedure to handle both situations.
Okay, good, because that's what I was going to ask you. If you have a priority of your objectives, you have primary and secondary, and even when you're mentioning different tethering options, if that's not high on your list of priorities, make sure you can down select, but you've got a preferred way to go into that, and then you've got a backup plan. And if you have those identified up front, you'll be much more efficient.
Yeah, okay, that sounds good. Thank you.
Another question for you, Matthew. On your eye bolt / handle, did you guys consider that graspability with a gloved hand?
Yes, definitely. The intention behind the design is not actually to wrap your hand around it. It is to firmly press your hand on top of it to keep the device secure. And the edge of your fingers can then slot next to the feet on the device. So the actual design is not to grab, which definitely would be probably not possible with the astronaut gloves, but instead to rest on top.
And that distinction is outlined in your preface?
Yes.
Okay.
Sorry, I didn't hear that last word, but it's in our procedure.
Very good. Thank you.
All right. So here is now a step-by-step breakdown of the operations plan. Kind of a condensed version, but the summary of what we plan on doing. First, the diver will drill the coring sample. We will work through them towards understanding how to align, how to prepare, and how to test and make sure the drill is functioning properly. We will verify that it is properly no longer in transportation mode and in the operation mode. We will engage this step by having them first test the drill on its own and then slowly lowering the drill into the surface to initiate the contact with the surface and start the removal process. Once we've gotten there, we will continue on with sample removal. We'll go down to the 3-inch mark, which is again both marked visually as well as just mechanically through the wider diameter at this point in the drill bit, so it will automatically stop for the user. And at this point, the user should, which is noted in the procedure, should then shear the sample by dragging parallel to the surface, a horizontal movement, and then they can then slowly, perhaps through slight movement of the drill still, extract the sample out of the test bed, and then the user can then use pliers to take the sample out of that drill bit. Once that is done, once the sample is extracted from the drill bit, the sample can then be stored within the plastic containers found on the storage belt, and it can be closed for then continued use. At this point, or perhaps earlier, we can assess whether or not, based on time constraints and how things have gone so far, whether or not we want to continue with the process. And later on, we can evaluate how the operation went, how the diver is feeling, both fatigue-wise and risk-wise, and if things felt unstable. And again, these checks will be made throughout the process to keep things safe. And again, we will also assess the quality of the sample. We have a few different metrics we're thinking of. We have listed things such as whether the core sample is broken up or splintered, and so on. And we can go ahead from here.
And have you also identified the difference between your test subject operations and your technicians' operations?
I'm not entirely familiar. Could you clarify?
So if it's not an objective to install something with the spacesuit, gloves, and everything, if you do not want a specific aspect identified, but this is a setup procedure, it would be set up for the astronaut beforehand.
Right.
We want to identify that as making sure that we don't give you the improper feedback on your design. We want to make sure we understand your objectives and which are test specific and which are what you're really after design wise.
Right.
You don't have to answer that now, but just make sure you consider that and when you're going over the details of how you want to direct the entire team.
Okay, we'll keep that in mind. We have noted topside versus poolside, but I think that's good that we will highlight the technician versus diver approach as well to get that across better.
Thank you.
Absolutely. Okay, so now going into the technical requirements of the testing operation and a more specific breakdown of the testing that we have done on our end. So we have run 3 full tests, and through each test, we have successfully been able to extract a cylindrical sample out of sandstone. The changes made through each test were generally safety related, as well as just stability wise. Things like the implementation of that eye bolt, as well as which serves as a farther handle that keeps the hand of the diver farther away, as well as just a better understanding and breakdown of how best to operate the device. We were able to successfully both drill completely through a block of sandstone, as well as drill part way in and shear off the sample and then extract it. We found both to work pretty effectively. We also, through this testing, decided to implement the pair of pliers to best fit the ability to remove the device, to remove the sample out of the device. And there are also some very relevant issues to note. The first is that of walking, in which the drill head, the head of the drill bit slips around when trying to make that first contact with the surface. The device greatly reduces the effect of drill walking. However, it still does exist to a light and notable degree, and we found this best is mitigated through having the drill at maximum speed above and before contacting the surface and slowly lowering the drill into the material. And we've noted this in the procedure as well. And we found that slow but fast movement of the fast spinning movement of the drill helps to greatly reduce this issue of drill walking. And through our testing, we've reliably been able to initiate that first groove within the sample. And once that's made, there really is that issue is no longer a concern. Another thing worth noting that I believe is not on the slide, but is definitely worth mentioning, is when the drill catches within the material. We have found this to happen occasionally, usually due to, if it is to happen, just due to user error of slightly tilting the device a bit. But this generally does not pose any significant issue other than just requiring a slight pulling out of the drill and resuming the process as needed. Once that initial groove is made, the diver can remove the handheld drill and device whenever they want and initiate again as needed. And so just then resuming the process has proven to not really be a problem when testing. And through this testing also, we noted that there's really no signs of loss, damage, or losing stability when testing. It seems to be pretty reliable so far. And we can go on to the next slide.
And similar comment with all these off-nominal situations you've identified, make sure those are very clear in the briefings, that these are alternate methods and what to look for, especially if there's any warning signs for these things.
Okay, sure thing. I'm not sure if these videos are playable. If it's convenient to do so, we can maybe just skip through a few seconds with each clip. We have 3 clips, just to give an idea of what this looks like in person. So here is the attaching the eye bolt onto the device, and the coring bit is there on the table. And so this coring bit gets inserted through the bottom of the device, up through the bearing located on the top, on that top plate. And it's from there that the drill chuck can then attach onto the device. And I think that gets across the idea of assembly. So we can go to the next video.
Did you have any difficulties achieving a coring sample 3 to 4 inches in length without the drill binding as it progresses down in your fixture?
Through testing it, but if by binding, if I'm thinking of the right thing, as in it kind of gets stuck when drilling.
Well,
that did happen.
When the drill bit walks, it's going to be not perpendicular to your coring surface. And so as that plate moves down in a perpendicular fashion, it's going to bind that opening to the opening where your drill enters the substrate.
Oh, are you saying that the base plate kind of sticks itself tightly, slightly unevenly onto the drilling surface?
If the base plate is parallel to your drilling surface as shown here, and the drill bit catches anything other than directly normal to that surface, then as your bearing surface up above, just below the drill, walks down, your drill is going to be cocked, right? Because it catches a little bit. It's not
At that slightly diagonal angle, you're saying?
Yeah.
So that is definitely an important concern. We generally the bearing and the way that the drill shank is lined up keeps it quite parallel. It is actually on one of our tests, it was noticeable that there was a bit of an angle, and this is definitely a relevant concern. But we found that there's a little bit of room for a little bit of available room at which this angle doesn't really pose much of an issue, and we were able to successfully extract the sample. Although that is definitely something we probably want to check during operation and to verify from the very beginning if we have made a perpendicular alignment.
Okay.
All right, we can play that video. Maybe just a few seconds of it. This is just drilling through, and then maybe skip around to, let's see.
And again, do you have areas of touch, no touch? We'd like to make sure those things are identified.
Yes. And by the way, we can maybe skip the video to maybe 2/3 of the way in just to see what it looks like later. The intention is to not have any hands or fingers inside the red ring, which is that noted through the tape. Aside from that, that is generally the no touch area. And we can maybe skip towards maybe the last 30 seconds, last bit. yeah, and then we extract the sample and then use the pliers to remove it. I think that covers the idea. I think there's one more video as well. And then here we remove the sample with the pliers, which is the small kind of add-on. And as you can see, there's those two holes in the side of the device, and that's the angle through which you can access the coring sample. And it's pretty firmly locked in place, so it does generally need that kind of push from the pliers. Okay, and then maybe skip a little bit ahead. It does take a few. Yeah, I guess we kind of missed it, but yeah. So that's the sample then removed from the coring bit. I think that's good. I think that gets it across. So we can move on. Okay, and then here is a breakdown of our hazard analysis.
Yes, a couple questions from the
Yeah,
high
absolutely.
One, did you have material striking your hand as you drilled? Because there's nothing to directionalize the debris that's created.
I did not when testing. There was dust, like powder, but from what we observed, the testing did not stir up any sizable amount of debris that could pose any risk of damage. It was a very fine powder. That might change. The testing conditions might change with different materials, but there was not any worrying amount of debris or offshoot that was hitting any part of me.
Okay, and our second question is, looking at the tool, it looks like the only thing that keeps that top metal plate in place is those rubber caps at the top of each spring. Have you had any problem with that plate coming free and those caps not being able to retain it in place?
That's correct. The only things holding it are those two caps. I have not had any issue on the up pulling up and popping out those caps. The thing to note is that these springs don't in any way stress on those caps, so it would be quite difficult to the springs will actually at a point provide negative, or I guess negative pull, I guess, in. So you'd have to be pulling against the springs in order to have any chance of popping out those caps, because the springs are attached securely up to the top of the base of the upper plate as well. But yeah, that's the situation with those caps. Okay, if there's anything further on that, we would be happy to take a look or address it as we can. Okay, so then moving on to hazard analysis. So these are the main hazards that we had in mind and that we addressed through our testing and changes that we've made. The first was that of simply the materials and things like stress corrosion, but through what we've assessed and the materials that we've chosen, our materials are good and reliable for any scenarios that we'll be putting the device under. In addition, a relevant concern is that of the rotating device. The device, the drill bit could certainly get stuck during operation, but we have put in controls to make sure through our operations plan how to address if this happens and how to mitigate any risk or damage that can come from that. Specifically through proper engagement with the material and proper contact being made. Another notable risk is that of stored energy through these compression springs. So these compression springs do pose stored energy when they are pushed downwards, but when compared to the weight of even just the handheld drill itself, as well as the expected force used by the diver, this will be greatly, this will be a very small concern, as the springs do not pose any real risk of overshooting or springing back up too far than they need to, and their maximum distance is distinctly below those top caps, so it should not pose a risk. In addition, we've added those wraps around the springs to avoid finger entrapment, and also just to prevent any possible damage from that. And then lastly, the last concern we're highlighting is that of sharp corners, edge protrusions, and so on. And through our manufacturing, we have done what we can to mitigate any sharp edges, and also where any potential edges do exist, we've added extra tape to ensure that no harmful contact can be made. And we also have those keep out zones highlighted with red tape. We can move on to the next slide. And if there's any questions on the hazards. Okay, great. Do we have a slide after that? Okay, maybe this was, oh, there we go. And then we have some notes on feedback we got from the TETP changes that we made, specifically based on that. There's kind of a highlighted look through, but generally speaking, we improved on safety. We added a few things here and there, namely the eye bolt to keep users' hands better out of reach, as well as the various ways in which we've implemented safety measures to keep the user safe and to keep them to keep risks of damage out of the way. And I believe that covers what we have for the, oops, for the TRR.
Okay, thank you very much. From the room, any other questions? I think the only couple things I had on here, honestly, you've already identified, talking about delineating specifically between what you want the subject to actually do and evaluate versus what you'd like the technicians to do and as part of the test specific stuff. I think you've got that. Identifying your, I'm not sure it's really an action, it's more on you, suggestion to identify your test priorities. You've got a number of different ones, hit the highest ones first. So because you don't necessarily have a whole lot of time. So I don't think that's an action, I think that's a suggestion. And then I got to be honest with you, you know, you've identified some hazards and you've already made some engineering controls for those. That's a very good process. So that's really good to see from that standpoint.
Thank you.
Anybody have any other any actions for the team here? That's really all I captured. Just I'm going to take that silence as that. So very, very much looking forward to seeing this in operation. With that, Ron, I think from the NBL's perspective, I think we've completed what we need to do here today, correct? And what do we need to do now? Ron, are you clear for the day, or what do we need?
Those are all of the TRR presentations for the day. So we are done.
Okay. So we look forward to working with all of the teams on closing out these actions expeditiously, and more than anything, getting them in the water. And I know our dive team is really anxious to jump in there and start playing with all this kind of stuff and getting you some good feedback to drive those designs and some really interesting ideas we've seen here today. To the review committee and all the associated folks that are online here today, thank you so much for hanging in there. I know we ran over a little bit of time, but again, this is good stuff. You know, not only for the teams and moving them forward, but very thorough, and very, very, very much appreciate all your extra effort and attention on this. Ron, unless you've got anything else, or Gail, I think we can probably close out for today.